Hello, and thank you for joining me on this guided project. This is the second guided project for our linear regression modeling units. And today we're going to be doing house price predictions on this advanced regression techniques uh, project from Kaggle. So you can follow it here. And today what we'll do is I have the whole workflow set up so you'll be able to submit predictions, and you can submit predictions here and just drag and drop into this place right here. You'll be able to see your score and see how well you do. Hopefully you can improve upon my score. Okay, so first step, mount the Google Drive. And the next thing, we're going to import a library. So kind of our standard imports right here. We're also going to do PCA and standard scalar. We're going to work with linear regression mainly in this unit. So we'll do linear regression. You'll be able to switch that and change for your final predictions. Because this is for a competition, linear regression generally isn't always the best. It works well, but it's not always the best. So I tried as well gradient boosting and bagging regressor, which are two of my favorite ensemble methods, to give those availability should we decide to use those for our predictions in the competition. So we do train test split, make pipeline, and validation, cross validation score. And we're going to import warnings and then ignore the warnings, just because with sklearn we can get a lot of how would you say, a lot of warnings, and so just to kind of avoid all the extra clutter. So what we'll do is we'll start off by importing our data. So I have these on my reservoir in GitHub. So you'll be able to you won't have to download the CSV, you'll just be able to import it directly from here. So what we'll do is do your standard workflow to start this off. So we'll do pd.read underscore CSV equals to train. And train is equal to the address of the CSV file in my GitHub reservoir. And so you'll be able to access it right from here. And then we can do the same thing for test here. So we'll do pd.read underscore CSV and import those files right here. In the next one, we're just going to keep the test IDs because you need those for our final workflow in our final prediction. So we're going to have a train test. We're going to have a train data set that has the final examples, has the test, the actual Y values. And then we have a test set that doesn't have the Y labels, the target value. And so we're just going to save the IDs here and we'll use that later on, but we'll be working with mainly the train set today, but we will see the test set in all of our pre-processing workflow so that it's done the same for everything. So first thing we'll do is we'll check the shape of our data. And so we're calling it df. So df.shape, and this is just an attribute, so no parentheses. And we have 1,400 rows and 81 columns. So it's a big data set, and I think an overall theme that we'll have to be conscious of with this data set and kind of all of the stuff, as you take this project to the next level and, try and improve on my predictions, you'll always have to be conscious of the number of features. We have quite a large number, 81, and lots of these are categories, so we'll end up making even more than this. And so we have to be conscious of this in terms of not overfitting per se, but too many features really just tends to not give us a good prediction on our test set. It can look good on paper, it can look good on the training set, but it doesn't generally give good on the testing set. So we want to make sure that we're reducing the number of features, and that's kind of the theme for this project, will be how do we reduce this number to keep it in the smallest number possible, because we'll likely end up going into 150 or something after we've gotten dummies from this. We've one hot encoded the categories. Anyways, so we have a lot of features, which is kind of typical for a housing data set, but we only have 1,400 rows. So we have a lot of features and not a lot of samples, which is kind of bad on both ends. If we have lots of features, it's okay. If we had 10,000 or 20,000 or 100,000 rows, 81 would be a much more reasonable number. But for 1,400, it's usually a little bit too much. So next what we'll do is we're going to inspect. This is a very simple thing to do, but it's just it's so valuable to just make sure you check it really at the start of the workflow. And really the biggest thing that you want to hear is see where are the null values occurring. So we have 1,460 values. We should see 1,460 in all of the non-null values. You can see some of them have non-values, and so that's a good hint to start off. Also really inspecting what is the data type. You really want to be looking here, where is there an integer, which column should be an integer and is actually an object. So that will let you know there's something wrong. There may be a question mark for a null value instead of a null value, and that will change the type of that, the data type of that. So we'll have to be conscious of that because it will affect our models won't work if we do it that way. So very important, very simple, but it's good to go through that and check. And really any workflow, it's good step in understanding your data. So here what we're going to do is we're going to plot out the distributions of our data. So as we just saw, we have some objects and we have some integers. And so being conscious of that, we're going to do a workflow to try and do all of the columns at once. A little bit more complicated workflow than doing everyone by itself, but then you don't have to write many lines of code. So what we'll do first here is we'll start. So to start this off, we're going to go for feet in df column. So df columns gives a list of all the column names. So for feature, for column, for feet in df columns, we're going to plot a figure size, and then we're going to go if df feet. So that feature, every one of the features, is the data type is equal to, well, what we want to see here is an object, because for objects we'll do something different, and for objects we're going to use so we'll do SNS dot count plot. Very similar to the idea of value counts in Panda. So data equals df, and then we'll go x equals feet. Okay, and then for our dis plot, what we'll do is we'll do SNS dot dis plot and data equals df, and then x equals feet. Okay. And for our plot title, so you can see here we're going if it's an object, we'll do a count plot. If it's anything else, so else, if everything above is false, we only have one if statement here, but if everything above is false, then we'll do a dis plot, which will work because the only thing that will be left will be numeric features, integers, and floats, so we'll be able to do this. And for our title, what we'll do is we'll put in feet as well. So it will give us the name of our title because we're plotting this many together, it won't plot properly to see this, so get a nice plot. Get our IDs, which is pretty consistent. It's really important to expect this. We have quite a few, so I won't go through everything in detail. And that's maybe one thing to kind of be conscious of is there's just almost too much with this data set. So you could get lost in every single column and really understand exactly what I did. I tried to do this at a very conscious level of trying to really focus on reducing features. Well, I wasn't able to spend hours and hours researching every category feature. And so this will be something you'll see there are quite a few categories that maybe some are obvious. This is our alley, so gravel, alley, paved. That makes sense. But here, lot shape, reg, IR1, IR2, IR3. I don't know, right? And so one of the things that we could just, in terms of reducing our features, reg could be one, and then we can move these other three categories into one. So we'll reduce it, and then we'll reduce the number of features that we create when we're one hot in coding. So you could spend a lot of time, but really here we're just trying to do things a little bit quicker in the sense because we have a lot to deal with. So you can spend time researching exactly what all of these categories mean. And if this is for your job, you would want to. If this is for a fun project for a competition, you might not want to spend as much time. And the idea here is focusing on which would make sense to combine, and then only doing research where it's necessary. So going through all the features here, we got quite a few. And you'll see my notes here on all of the features as we go through that. So I wrote kind of notes of which ones I wanted to clip to deal with the outliers, the other ones that I felt would be appropriate to bucketize, and then other ones to do dimensionality reduction. Now, this can feel a little bit like a school project, but really these notes are just to make your life easier, right? And so if you do these, they will, you won't have to go back and inspect every one of these plots because there is 81 of these plots, and it can be hard to even find which column you're looking for. So just quick little notes like this, as to the point as possible, can be very valuable and just letting you know kind of your to do for the next step of your project. And so it's kind of a list of pre-processing what you'll need to do, and then going into the bivariate analysis. So because there's so many, I didn't do a pair plot like I would normally do in this data set. So what I can do here is I'll go df dot core with, and what I want to see here is the correlation with, and I have to give it this series of what I want to see the correlation with. So if sale price. And then just an important thing, it's always good to sort the values here. So because they'll just kind of be just organized hodgepodge of values. And so if we sort the values, you can see which ones have the lowest correlation and which ones have the highest correlation just from the get-go. And this is really, really important for understanding which ones would be the valuable, because we'd be looking here for which ones are unimportant. Well, I would say something with a negative 0.01 or negative or positive 0.04, 0.04. These ones probably are less important. And so we can start to develop a theory. We'd want to test these, but develop a theory about which ones would be the most valuable that we'd want to keep in our data set. So here what we can see is we got this, but what if we just wanted to look at the values that are greater than or less than a positive 25 correlation? So we're going to get our series and we're going to logically index on this series. So what we'll do is we're going to do two, so this and this. So if they're, or sorry, this or this, and that is not an or, this is an or. And so what we want to do is we're going to do when each one of these, so when sales price core, not so much, we don't need to sort values, but what we want to do, so when this, our first statement, when this series right here, when it is greater than, so let's actually, so when this is greater than, or less than, greater than 0.25, or, and we'll just copy this. Ooh, I have an extra. Okay, and so we're just going to copy this. So yeah, the stuff inside the circular brackets, and we'll copy and paste this in the other circular bracket here. So there's dual logical indexing, and we want to do greater than 25 and less than, sorry, this one should be less than negative 25. Show the features only less than 25 or positive correlation. And so sorry, what was it? 25% positive correlation and negative. So less than 25. So actually, sorry, I did this wrong. So we want to show greater than negative 25 and jumping ahead of doing the one before this and less than, we see is we can see greater than 25, less than 25, and we have our values here 0.25, 0.35, and we can see the kind of the most unimportant features. So things like the ID would make sense for not being important. Low quality finished square feet, also very unimportant. Years sold seems to be very unimportant as well. And other things like basement, half bath. So again, just kind of developing a theory of which ones we would want to get rid of. So what we can do here is we want to see the next one, only correlations that are above or below positive 0.45. So what I'm going to do, I'm just going to make my life easy and do professional coding. I'm going to copy and paste what I have up above, and I'll paste that down into these square brackets right here. And what I'm going to do is make some changes here. So we want to see if it's 0.6, if it's greater than, or sorry, it's less than negative 0.6, and it's then greater than 0.6. So we want to say or, and so this one is, so we notice the above one is in between two objects is usually an and here it's an or. So we want it to be greater than or versus less than this and less than this. Or we want it to be greater than or greater than. And so here what we're going to do is then sort the values. And so you can see here we get all of the values. We have no negative correlations that are more than negative 6 you can see that from here. Our lowest negative correlation is 0.35. But anyways, now we have a values that we can interpret, and now we have our most impactful first floor square feet, total square basement, garage area, car garage, greater living area, overall quality. So these all have a higher relationship with our values. Okay, and so just writing some notes here, which ones have the lowest, the highest correlation, and again, just for you to reference and come back to.